Welcome to today's seminar with Magnus Myreen, who is working on, I think I'm correct in saying sort of formal verification broadly, or program verification.
Yes.
But I think what we're going to talk about today is sort of sometimes maybe you can't verify the programs, but you can verify that they at least do the correct thing in the sense that they give the correct output, and maybe that is also good. And so Magnus is going to take us through a tour of verified proof checkers. So please, oh, and I should say that Magnus is at Chalmers University of Technology, but which you already see from the slides. And then I should stop talking and give the floor to our. So thank you. And
thank you.
And the floor is all yours.
Thank you, Jakob, for the invitation. So I want to. I'll mention work done in collaboration with many people, including Yongkiam Tan, who is here. I saw in the same video call. So particularly in the next part of when we go to technical details, I'm sure he will also be more than happy to answer the questions about the technical parts. So what's I should mention that this is a bit of a hodgepodge of various things. I've been doing a sort of introduction to my work in general. In some parts there will be too much, some sidelines and too much detail, but we can sort of skip over some of the detail and come back to it if there are questions about it. But my aim with this talk is to start new collaborations. So this sort of give a flavor of many things that I've been up to, and then see if that sort of tickles someone's interests. Okay, so let's talk about them then. So I should start by saying that I'm very much sort of doing research using and with interactive theorem provers, and specifically Hall 4. Earlier in this seminar series, there was a talk about Isabelle Hall, and I use a different prover called Hall 4, but the logic is essentially the same and similar concepts. And within this, I work on verification of functional correctness of programs. And then say maybe a bit peculiar to me is that I do of actual code. So what is that? This kind of stuff. So what is this? This is ARMv7 machine code. I mean, I'm not specific to ARMv7, but a theme throughout my work is that I like to verify things down to the machine code that actually runs it. Not necessarily at that, originally at that level, but all the way down to it, because that's what actually runs on systems. Yeah, so this is because my PhD was on machine code verification, and since then I've been sort of going up in abstraction levels. But now I thought I'd start with a little bit of a sort of interactive part and say, well, what do you think you can compute, or one can compute with these 4 instructions? So there's 4 instructions. More, you can't really read it much more than that, but I'm happy to hear guesses if someone has. Okay.
Loading 2 numbers and adding them and then outputting the answer or something.
No, more interesting than that. So I could give you some hints. So line 1 compares register 1 with register 2. Line 2 is conditionally executed. If line 1 gave register 1 is less than register 2, then it subtracts register 1 from register 2. And then the third line, if line 1 gave that register 1 is actually larger than register 2, then register 2 is subtracted from register 1. And if line 1 gave that they are different, then this instruction will jump up to the top. So it's a loop. So here's an example.
So GCD?
Yes, that's right. I thought this is a cute piece of machine code. It's very short, surprisingly short, I'd say. So, but of course, I like to verify things down to the level of machine code, but no one actually likes to program there or, doing verification at that level is usually too much. So actually what I've been working on is proof producing decompilation tools proof producing compilation and verified compilation. So this is sort of the theme of my work. And well, what are the uses of these? Well, to verify programs that are proved correct down to the concrete machine code, and examples of that is then verified checkers, because they're very good examples of things that one can verify, because they have a good specification, a clear specification that one can state, and it actually has some value to verify them, because then you can trust your checker even more if it's verified like this. So this talk, I thought I said it was going to be a bit of a hodgepodge of things, but I'm going to give sort of an introduction to sort of my way of working, and then talk about verified checkers afterwards. And then, well, because I don't really know my audience or your backgrounds, so that's why I'm going to sort of start from basics. And so if there's any questions, just ask, or if this is too trivial or something like that, then rush me on. It's all fine. Okay, so I thought I'd talk a little bit about this verified compilation business. So what is it? Well, a verified compiler comes with a machine check proof that for any program which does not generate a compilation error, so the compiler succeeded, then the source and the target programs behave identically. And that's the sort of key of a verified compiler. So if you read about them, you might see that sometimes they're called certified compilers, but I think that's misleading, and one shouldn't use that term. So then, more on this topic of verified compilers. What's the motivation for them? Well, imagine your program crashes. Where do you look for the fault? Do you look at your source code that you gave your compiler? Or do you look at the code for the compiler that you used? And of course, users of compilers really like to rely on their compilers to transparently transfer behavior of the source down to the target. So users always want to look for faults in their own source code rather than the tools they use to get the executable. So then one might ask, well, in my experience, compilers don't have errors, and they always are reliable like this. So you're always in the first option here. But that's not quite true in general. So all compilers have bugs, as this paper showed. So this paper from 10 years ago showed that every compiler that these guys tested was found to crash and to silently generate wrong code when presented with valid input. And there's one exception, though. The verified part of the CompCert compiler is the only compiler we have tested with CSmith, for which CSmith cannot find wrong code errors. And this is not lack of trying. They spent 6 CPU years to the task. So they really tried to hammer this one, but couldn't find any faults in it. So even if you don't quite believe in all the specifications of the language or the methodology used to verify the compilers, the results still seems to be in empirical tests very, very robust. Okay, so I'll just talk a bit more on this topic. So I've said what to have a verified compiler is to prove the compiler produces good code. Why? To avoid bugs, to avoid testing of the compilers, which can never be complete. And then how is something I thought I'd spend a few slides on. Maybe it's obvious, maybe it's not. As I said, I really don't know my audience here. So feel free to ask any kind of questions, both beginner questions or expert questions. So this is the next few slides.
So one beginner's question, but maybe this is premature and you'll get to it. And you maybe hinted at it a little bit already. Like the end goal, are you selling 100% definitely absolutely correct code, or do you view this more as well, I'm much more confident now because I went through all this formal rigor and I probably would have caught errors, but at the end of the day, who knows?
I wouldn't say you get absolute guarantees because there's assumptions you make in the proofs. We'll get to those assumptions in a moment. I mean, you get absolute rigor for the things you proved and you proved about, but whether that reflects the real reality is something, you know, there's always a little gap to sort of the real running system. But what I'm saying is, what I tried to make a point with the previous slide was that in empirical tests, the product you get out of these verification efforts is extremely good compared to what's produced by other methods. So even if you don't believe in the tools used here. Okay, so proving a compiler correct, here are the ingredients. So before you can even start, you need to have some kind of logic, formal logic for the proofs. So here, well, students tend to know first-order logic, but I don't think that's enough here. So, well, I use higher-order logic, classical higher-order logic. And then another ingredient you need is accurate models of the source language, the target language, and the compilation algorithm. And here is these are, of course, only models of them. And this is where you have this sort of slight gap possibility. For instance, your target language, what is actually running on the CPU, that might not be exactly what the CPU runs. So there's one possibility of a little gap where something might go wrong. So why do we need this? Well, proofs are only about things that live within the logic. So we need to represent all relevant artifacts in the logic before we can even start. And when you go for a real source language and a real target and a real compiler, there's suddenly a lot of details, well, to get wrong. So then to make this all possible, you have to use a proof assistant to manage this. And so a proof assistant, what does it do? Or an interactive theorem prover, it's a mechanized proof assistant ensures that we do not accidentally skip or overlook details. One can maliciously trick it into doing things, but I'm pretty sure it's very, very, very difficult to accidentally sort of trick it into doing something, skipping some step. And it's possible to afterwards check whether you've skipped a step or not. So now, just to make this a little bit concrete, I have a few slides just to sort of show what all these ingredients look like and what the tool looks like. I thought I'd show that. So first of all, we need accurate models of the programming language. So we need the syntax defined, what it looks like, and the semantics, how it behaves. And for what the semantics of programs is usually, I like to think of it as an interpreter based on the syntax. And that's how I tend to write my semantics. So there are major different styles of program semantics. Well, there's big step and there's small step are two flavors of them. And in the next few slides, I'll give you examples of these for very, very, very basic programming languages. So in the big step, for big step, we'll use in this example for the structured source semantics, and the small step will be for the unstructured target semantics. So source language and target language. So the syntax of the source is this one. So an expression is either a number, so this is then a natural number, or a variable, which and then a variable name, which has a name, or a plus of two expressions. So you see this is recursive and can be arbitrarily deep. Okay, and then target, so in citations, machine code, this is not quite machine code, but it's some kind of low-level instructions. So here you can assign a natural number to a register name. You can move the content of a register name into another register name. And you have an add instruction that, given two register names, can add them and add the result, or store the result in a third register name. And the idea here is that a source program is then an expression, and a target program consists of a list of these instructions: const, move, and add. So in this, so now that's the syntax. The semantics here is the big step semantics is defined as a relation defined by rules. So we have a rule saying that a variable s in an environment evaluates to a value v if you can look up in that environment for that variable name and you find v, then that evaluates to v. A constant number evaluates regardless of the environment directly to that value without any premises. And then add recursively evaluates each part, x1 and x2, and they become v1 and v2, and then the result is v1 plus v2. This is pretty much the simplest operational semantics one can have.
So on the left here, we're like living in the programming language, and on the right, we have some logic that I guess is rich now. It contains integers and stuff. And
yes, so here we have the program expression and environment, and this is then a judgment of this, saying that okay, this this rule says that this it reduces to this value. Yeah, so this is the mathematical integers. Yeah.
Okay.
Yeah, so that's the source semantics. And now let's have a look at this target semantics. It's a small step semantics. So it's so big step. It's called big step because it's sort of, if we go back to the big step semantics, it talks about one such relation talks about the entire evaluation of this expression all the way to the end. But small step semantics is doing everything in small steps instead of one giant leap to the end of execution. So here we have a step that, given an instruction and a machine state, gives you the new machine state of after executing this instruction. So we see the constant n just updates. So here state is a mapping from names to values, register names to then register values. And here we see that const, all it does, it updates the state function so that it's the same as state, but updated so that s maps to n, because that's what we stored. Move is very similar, but now instead of so having n there, we look up we apply this function state to the value to the name s2 and get the value from there and update s1 to b. It copies it over. And add is very similar, but now it does an addition instead. And then we have a list version. So this is then running it over an entire program. So here we have steps. If you have no program to run, then the initial state is the final state. If you have one instruction followed by several more instructions, then, well, you run step to get the state after one instruction, and then you run the rest of the instructions. This is recursively defined. Okay, so any questions about my target semantics or my notation? If not, then I'll go ahead. So then we also need, so now we have a source semantics, a target semantics, now we need a compilation function. And here is my simple compiler function. So compile, here we want to compile the constant expression, and we give the compiler an argument as well, saying that we want it to store the final result at register n. And now register names are not just natural numbers here as well. So it's a bit of a strange machine, but still it works for our little example. So here, if we are to generate code for this, then the const instruction is good for this. Did I get that right? Yes, that's right. So it stores the constant k into register n. It was given the result should go into register n. And here var is now doing something very similar, but with a move instruction. So it looks up the value of register v and moves it into n. And there's an assumption here that the variable names from source match register names in the target. Okay, plus is clearly the most interesting one. So here we have a recursive construction. So x1 and then x2 have to be added together, and the result should come out in n. So we can compile the code, compile expression x1 and have the result go into n. And then we can compile x2 and have the result go into n plus 1, the register name n plus 1. And now once we've executed this code and that code, we should have a point where the value for x1 lives in n and the value for x2 lives in n plus 1. And so we can do an add instruction using n and n plus 1 and store the value in n, which is required from there. So, okay, so this is, yes, a few comments that I've been saying. We use names above n as temporaries. This is what we're doing here. So for this to work, this relies on variable names in the source match the variable names in the target, and no v, so n will always be larger than any variable v we will come across. So yeah, this is the simplest possible compiler. Now I thought I'd show you what it looks like to have proved a correctness statement for it. So here is a correctness statement for it. It takes a little reading. So we say here, for every evaluation in the source semantics, so for any expression and any environment, for any result that it manages to produce, then we have for target state and k, we then make an assumption here. The assumption says, if we can look up something in the source environment, then we can find the same in the target state. If you evaluate the target state function at that address, that index, then you get the value that's in the environment. Okay, and then here comes the crucial part. If we run steps, so our target semantics on whatever the compiler produces for this state, then we get a state for which, when we look at k, where we wanted the result to come out, then we get exactly the result that the source semantics was computing. So this is saying that indeed the result of applying the compiler produces code that correctly computes exactly what the source computed. And then the last part is just a clause you have to add to make the induction work. The lower part of the state is left untouched when you're by the compiled code.
Sorry, I'm trying to parse this. So the last three lines, like the third line from the bottom, is X is the whole program, is it?
Yes, that's right.
Okay.
The source semantic, source program, yes.
So X is a source program and you're compiling it?
Yes, to a list of instructions here. K
is a list of instructions. And then you're saying that you run the step function on this?
Yeah, and the initial machine state.
Yes.
And then I get a new machine state, which I bind to this.
And the environment said in that environment that it should evaluate to res, and therefore the machine code also evaluates to res, which is exactly what we wanted to happen.
Yeah.
And then the last line is something that you said you want for the induction.
Yes, for the induction. This is proved by induction on the evaluation relation. And here you say, this last line says that the initial state and the resulting state in those, nothing is changed underneath K. And K is this argument added to the compiler. So we didn't change anything. We only use temporaries above K, at K and above.
Mm-hmm.
So I was thinking of, I don't know, I might have used too much time, but I was going to show just how this looks very briefly in the prover. Oh, yeah, so this is too small, probably. No, this is, oops. So this is, I'm going to make that slightly larger. That's too big, maybe. So this is what it looks like. It's exactly what we've had on the slides. Expression, instructions, then you have the evaluation. This was a down arrow, which is the standard syntax. And I wrote it in infix on the slides, but this is what it would actually look like. Because, well, I think you can get the down arrow also here, but I haven't managed to. So now it's a prefix operator instead. But you can see the same thing. So evaluation of this plus, it requires evaluation of each component, and then you get the result is V1 plus V2. And otherwise, everything looks just like on the slides. And okay, I can try to get, oops. And here is the prover talking, and I can go all the way here. And now I'm just loading it up. But this is the statement, and the proof of this statement is these 6 lines of incomprehensible tactic script. But maybe one thing that's sort of interesting to look at is that this is, now I've set up the goal. It says initial goal, and now I have to prove exactly what we have had on the slides. And the way to do it is you do induction on this thing, on the source evaluation, on the rules of the source evaluation. And then I'll just, okay, then I get 3 goals. It doesn't, I'll do this one as well. So now I get, and I'll do that too. Actually, I'll start again. So that, so now I have 3 sub goals, and one for the num case, and now I rotate to the next one for the var case, and I have just the normal assumptions here. And for the plus case, I get the inductive hypotheses for each sub-expression. So you see plus x and x prime, and I get 1 inductive hypothesis for x, 1 for x prime. And I won't go into the detail of this proof, but one expands the compile and the steps, definitions, and then I think the only hard part or interesting part here is instantiation of the second inductive hypothesis requires a little bit of proof that you actually satisfy this this assumption on going into it. And yeah, so this is what it looks like. And I think in the more technical part, we can come back to this if there's interest to have a look at it. But otherwise, I think I'll just continue on with the main.
Just one quick question. I don't know if it's relevant at all, but if you go back to the proof, like this FS compiled, FFS apply update, like these magic lines, would you, like if you're actually doing something real, would you talk to the proof assistant and hack around and it will sort of guide you to these lines, or how does it?
So the way I would, so this is what quite representative of what a proof script looks like. So this is pretty much incomprehensible to read unless you're seeing the proof state.
I guess like what I'm asking is like, would you just ask, hey, I want a proof of this theorem, and then the prover would go off and think for a while and it gives you this, or do you like interactively, you know, why don't you try this, why don't you try that, and then
exactly
you progress and get a nice lemma, and maybe this is useful, or?
It's not as automatic as I just state this and it tries. I have to go and do this So, but this is quite easy to write, certainly in this case. So I can talk you through what this is doing. This is just the definition of the compiler. This is the definition of steps. And this is the definition of a step, the single step. And this is just full simplification with these. And now I worry it might do too much, but it expanded many things. And well, maybe the inductive case was the bad one to start with, but maybe this one actually. Oh, okay, yeah. So this one, the constant expression, if you expand, compile, and then, okay, if we do one step at a time, I do just compile, then you see it expanded the compile, that became just const, because that was the definition. And then steps, if we add steps to it, it makes it just one step. And when we open step def, then it just becomes that. And we're nearly there, because now you're looking up k in a mapping where you just updated k to res. And so, well, this is obvious as soon as you sort of expanded this definition of what it means to update a function. And that's, I think this one will do it. Yeah, so that proved this sub goal. Yeah, so, well, this is the sort of interaction, tactic-based interaction. You start with the goal, you break it down into sub goals, and then you sort of, you simplify it.
Okay.
I just have a question, because I'm just wondering, wouldn't it make sense to just have that as a simple and always apply this?
Oh, the definition of the compiler.
Yes.
Yes, certainly. You can do it here, right? Simp here, and you get it. But here, this is a proof I'm using in teaching, and then I need to do one step at a time.
Okay.
So that it's clear, because if you apply all of these at the same time, they prove too much. This is often
Okay.
a problem with teaching interactive theorem provers, I find, because many tactics that people actually use do too much, and then the students didn't really see what the prover was doing.
Yes, and we're so used to just get the result out of it that we just get annoyed when, so I get annoyed when I have too much step. Yeah, okay, thank you.
Yeah. Thanks for the question. Okay, but I think I should really move on. So verified checkers. Many programs are, so why should we have verified checkers? Well, many programs are too complex to verify. For instance, modern SAT solvers. So the good news is that some programs can emit a log that can be checked by a verified checker. And these are, as I mentioned earlier, good candidates for formal verification because they have clear specifications, these checkers. And they also add value to the whole project. I will talk about, I've been involved in the following verified checkers. So the verified Milawa prover, which is a reflective checker for ACL2 style first order logic, and a checker for floating point error bounds for this static analysis tool called DAISY. Verified checker for open theory article files. So what are open theory articles? They're recorded whole proofs. And then a verified checker for LPR and LRAT proofs. So that's for UNSAT proofs from SAT solvers. So in this talk, I'll talk about these two. And yeah, so I'll talk about these, and let's start with this Milawa prover, which is maybe not your conventional checker. So the Milawa prover is, I'll get to the logic in a moment, but it's essentially, the Milawa prover, the core of it is 2,000 lines of Milawa Lisp code. And this then, we needed a specification for what it means for Lisp, this Lisp, give a source semantics for this Lisp that this is written in. And then we developed a Lisp implementation that can execute that. And then that is with respect to the semantics of x86 machine code. So this work was divided into two parts. One was to verify a platform, a Lisp implementation that could host this prover. And separately, there was this effort to formalize the inference rules of the Milawa logic that this implements, and then also formalize the semantics of it, prove this, the inference rules sound, and then prove that the Milawa theorem prover actually implements those inference rules that were here abstractly captured. So, and then the nice thing is here you get a really strong correctness theorem that brings all the way from, it relates the soundness of a logic down to the x86 machine semantics that runs your program. And there it assumes various things. It assumes that we got that right, and a little bit of C wrapper code and operating system and hardware. So not everything is proved, of course, but quite a lot is. So this project started through an email conversation with a guy called Jared Davis, who had developed this self-verifying theorem prover. And I'll get to why it's called self-verifying. So he approached me over email saying my theorem prover is written in Lisp, and he had seen that I had a paper on a verified Lisp implementation. He wondered, can I try your Lisp implementation for my prover? And I said, sure, why not? And then of course he asked, can it do this and that and that? And I said, well, no, it really can't. But then we started a conversation, and the interesting thing is that we collaborated, I think, for 2 years before I actually had even seen him. Like video calls weren't a thing then, so it was just email. Well, we started this conversation about, can Milawa run on top of my Lisp implementation? And we realized that this self-verification of Milawa actually is a very heavy process. It requires a 4 GB proof file to be run, and it takes, on the state-of-the-art runtime, it takes 16 hours to run. So this is a very heavy job, so to say. And so my little Lisp implementation was hopelessly toy, and we set off to do a new verified Lisp, which is able to scale to the point of running these large proofs that Milawa requires for its bootstrap. So a short introduction to Milawa, and this is work by Jared Davis, his PhD work. Milawa is sort of a proof checker for that is styled after theorem provers such as NQThumb, also known as the Boyer-Moore prover, and ACL2. But unlike these two provers, it has a small trusted logical kernel similar to LCF-style provers. But and LCF-style provers are provers like Isabelle Hall, Hall4, and to some extent Koch. So all of LCF-style provers tend to suffer from a performance degradation due to the sort of very conservative architecture of these provers. So I'll explain the architecture. LCF-style provers have a trusted logical core. All proofs pass through this core's primitive inferences. So this implements the logic that we're trying to capture with this theorem prover, and the core is kept really small, and it has to be trusted. But then you build a lot of infrastructure on top of that. For instance, first logic provers, decision procedures, rewriters, simplifiers, and any other custom tools like bitblasters or something like that. But all of these, when they do proofs, they build all their proofs through the entries in this core. So that's how these provers ensure that everything follows by the primitive inferences of the logic, because that's what the core implements. So this is a bottleneck for all proofs. They have to go through this core. So Milawa has a different approach. So yes, Milawa starts off with all proofs must pass the core, so a similar core, but the core can be reflectively extended at runtime. And this is the exciting part. So the first thing you do is you define a lot of derived rules, and then you start using them. You use the core to check that they are okay, and then you start using them as if they are the core. And then you keep on doing this. You use the derived rules to check more advanced things like case splitting and then rewriting and so forth. And you go up the hierarchy until you have auto tactics, and no longer do these go through the core, because they're all being proof checked, being checked by the core that they are sound. So you don't have to go through the core anymore, because the implementation of these is already checked. So what does it look like? This is some output from the Milawa's Bootstrap. So it starts by proving very basic things like defining not and verifying something about not, I think, termination. And you can see that this is a proof log. So this is the first thing it did. And then some 4,000 steps later, it does something called a switch. It starts with basic things. So up to this point, the basic core of the Milawa prover has been used. And now happens the magic, because this switch proof. Okay, so the last thing it proved before the switch was that I have a new proof P at level 2, a function called that I believe is a good proof checker, and it has proved that it is a faithful proof checker. And so then it does this switch event, which I think is very exciting, because it says, okay, I'm going to throw my old core away, and I'm going to now just switch to doing proofs with this new proof checker that the user supplied, which sounds so incredibly unsound, but it is actually sound. And I always think of this as someone essentially inspecting a new brain and saying, okay, this brain is good. And then the switch is when you suddenly take out your brain and put in the new, better one, and you're still, functioning. And then from then onwards, once this switch command has run, the new proof checker is used, and there are many of these switch events happening along the Bootstrap.
When you call it the extended core, do you require that what we had there before is also there, or is it actually like switching one core for another?
It's completely
unrelated.
It's completely switching one for the other, but of course it can contain the other one. Yeah, okay. I think in practice it does contain the other one, but there's no requirement.
Doesn't have to. Okay.
Yeah, and I mean, it's trivial to switch the proof checker to one that doesn't accept any proofs, because then it's immediately sound, but it's also useless.
Oh, so you don't have like a two-way sort of, you don't have soundness and completeness or whatever you would call it. You just want to...
You just have this, what you have to prove that for any proof that this new proof checker accepts, there is some proof that would prove the same statement for the original proof checker.
Okay.
Yeah.
But not the other way around.
No.
And when you bootstrap, would you also does the core already know all the logic that you need, or is it like somehow conceivable that the core has a simpler logic and then you sort of refine a richer logic on top of it, or no?
No. This is only about efficiency. This is not, yeah. So it's just more efficient ways of doing the same thing as the original core. You can't extend with you can't prove anything new with the new ones. That's sort of part of the soundness here. Yeah, so okay. So in the Bootstrap, you have 10 core extensions, and this builds up something that is somewhat similar to ACL2 in sort of expressive power of the proof checker. Yeah, so here, this is just a listing of what those do. But at the top, you do sort of conditional rewriting, for instance, as a primitive inference of the proof checker, which, if you talk to anyone from the Hall 4 or Isabel Hall, community knows, that is definitely not a primitive inference. That is quite a complicated thing. Yeah. So, and soundness was proved to be preserved here. And I just have the inferences of the logic here listed. Most of them are really, really basic, but there's a few interesting ones, like this one. A primitive inference is induction with respect to ordinals up to epsilon 0. So this is a very strong induction, and it's just a primitive inference, but we proved it sound. So it's all fine, but it's pretty strange to see in these kind of in here. Another curious thing was that you have base evaluation. So as a primitive inference, because we have Lisp here, or you can do things like this. You have natural numbers directly in the logic. They're part of the terms. The sort of they're directly there, and you have base evaluation you can use as an axiom. And then you have Lisp axioms saying that if you make a pair of x and y, and then you ask, is this a pair? Yes, it is a pair. So you have 56 axioms describing Lisp primitives, because this is a strange logic where really the terms of the logic are Lisp expressions. This is a sort of consequence of that. Okay, so to trust this, we had to prove that the logic is sound, the core implements the logic correctly, and the run executes the core correctly. And the result was, I would claim, the most trustworthy theorem prover, at least proof of the most trustworthy. Now I'm going to skip a bit ahead because I have too much detail here. Sorry about that. Okay, so yeah, well, actually the work here followed a quite standard, workflow. We specified the input language, the syntax and semantics. We verified the necessary algorithms, particularly compilation from source to bytecode, and from then bytecode down to x86 code. And to make all of this work, we had to have a garbage collector for the runtime and many things. So this ended up being about 30,000 lines of whole-for proof scripts, and I think it took about 6 months to do. But I'll skip ahead a little bit. Sorry for that. And then I will I'll show you 2 theorems about this, if I have the time. So this is the kind of theorem we get out. This is about the Lisp implementation. If we start with enough memory and I/O, and the program counter points at the code that we verified, then execution will either end in an error message like I ran out of memory, or it will execute an operational semantics for the source language, so the Lisp language, correctly, and produce a final state according to its semantics. And in this case, we simplified the proofs by only talking about terminating source programs. But this was fine because, this is part of the verified code. And now I'm going to show you, this is the final theorem saying that now we have instantiated the previous theorem with the verified checker. So if there must be enough memory for the Milawa kernel to fit, and the input has to be sort of on the input stream, the program counter points at our Lisp implementation. We either get an error message, or we get output lines that are true with respect to the semantics of the logic. So here we have, in the post condition, we'd say that, okay, we have, we get some output for this input, and for every line, we know that line OK is true, and line OK says if it printed that this is a theorem, then that theorem must be true with respect to the semantics of the logic for this context pi. yeah, so this is just really showing that one can get these sort of really end-to-end theorems, because this is talking about machine code at the same time as it's talking about the semantics of logic that it's implementing in the application that's running on top. And now, because I'm running badly out of time, I'm going to skip ahead and talk a little bit about this verified checker for LPR proofs.
Just to clarify, you're in charge of the program. So like if you want a few more minutes, you take them. So it's like...
Sure. But I still, it's good to keep to time.
Yeah, definitely. I'm just... Sure.
People expect meetings to be fit into slots. So this, the previous Milawa prover was, I would consider, a precursor to the CakeML project. So the CakeML project, I will talk in a bit, but this next verified checker is built using CakeML technology. So what is this CakeML that I'm talking about? Well, CakeML is a functional programming language similar to standard ML and OCaml. It's also, when we talk about CakeML, it's an ecosystem of proofs and tools built around this language, and a verified stack, so all the way down to hardware. So in this case, Verilog. So that's what we mean by CakeML project. So one of the key components of the CakeML project is that we have a very nice way of going from functions in the logic via a proof producing tool down to CakeML source abstract syntax. And then from there, via a verified compiler, so this is then a verified function in the logic, down to machine code. So if you write your checker as a function in the logic, which is a fairly nice way of programming it for proof purposes, then you can add a push of a few buttons. You can get down to verified machine code implementing exactly your checker function. So this is streamlining a lot of the sort of what was done maybe more manually in the previous work. So the CakeML project allows this. So just as an example, if we input the factorial function, then we get out here, the toolchain produces machine code that proves a theorem stating that the code behaves like the factorial function. And one of the things the CakeML project is famous for is that we have written a full end-to-end compiler that takes concrete syntax, parses it, does type inference on it, and generates code. And all of these are the blue boxes, so a function in logic. And notice that that's also the input for this part of the toolchain. So if you grab all of the yellow cloud and push it in there, then what you get is, if we input the CakeML compiler, we get out the generated code behaves like the CakeML compiler. So we have generated an implementation of the compiler itself using itself. So this is then called compiler bootstrapping. Now I'm going to skip ahead a little bit, and we can talk about that later. Oh no. I'm skipping ahead too much. So this is just a presentation about the compiler if you wanted to know more about it. Maybe what you can learn from this, just as at a glance, is that the compiler is non-trivial. It has many passes, maybe 30 passes it makes, and optimizing passes too. And there's a demo of it. Performance numbers of this, the generated code are similar to other non-verified compilers. So for instance, OCaml compiler is a sort of competitor to us, to say, so to say. It's a well-established compiler. Milton is a very good compiler. PolyML is also an established compiler. And you see that CakeML, the light blue one, is in the same ballpark. Sometimes it's a little bit slower, but in general, same ballpark in terms of performance as the others. So this is no toy compiler. So applications produced by it can be fairly performant. And speaking of, I'll have to skip these, I'm afraid. Speaking of applications, so here is the performance of the LRAT checker that Young-Kiam worked with using the CakeML tools. So here is a performance comparison of 3 different LRAT checkers. So here we have CakeML is the green one, an ACL2 verified checker is the red one, and a COC verified checker is the blue one here. And so the higher you are, the better. So CakeML matches the other verified checker in performance. So this is percentage of SAT race 2019 proofs checked. So how many we've managed to check, and with per instance time limit in seconds. Okay, so that's 10 seconds. It manages only that many, but then give it some more and it manages nearly all of them. Yes, so this is using the CakeML technology of translating functions and also doing more manual verification of CakeML source code. Young-Kiam managed to produce a checker that performs this well.
Do you want to say anything about how it performs compared to, say, LRAT trim or something like a standard?
I think I'll let Young-Kiam say that if he's still here.
Yeah. Hi. Yeah. So I think in this chart we're just comparing it to verified checkers, and the way these work is a bit, I think, quite a lot different from LRAT trim. And of course the performance is not going to be as good as LRAT trim, which is unverified and written in C. And actually the way like these checkers work is, generally speaking, they use a tool like LRAT trim that generates another proof, like an extended version of the LRAT proof. In this case, it's called LRAT. And then we check that LRAT proof instead. So the performance is, well, I don't think it's very comparable, except in our Taka's paper, I think we had a section also where we compared checking on a specific kind of LRAT proofs, where we managed to actually get within like a factor of 5 with a C version of the same checker. So yeah, that's what I can say about the performance in that respect. Okay, thanks. Yeah, I mean, it's clear that you might, I mean, having a verified proof checker is a nice thing, so you might be willing to pay for it, obviously. So I'm just curious, like, but it sounds like an order of magnitude, but it's not worse than that. It's kind of. Yeah, I mean, I think that the metric we went by was roughly with these checkers, the sort of the proof checking time is, I think, comparable to even the proof generation time in the first place, in the sense of generating the proof using a set solver. So it's not like you're paying a lot more, just to check the proof, in addition to solving the problem, the set problem that you have. I see. Thanks.
Well, okay, yeah. Well, I might as well show you this one because I haven't showed other demos, so I might as well. So this is running the verified program, and here it requires some input. So we give it a CNF file and an LRAT file, and then it takes a little time. I put time there so we see how long it took for 4 seconds to check this verified UNSAT for that. And then I'm just showing that the program that ran is really one of these CakeML generated ones. So it is, there's some boilerplate here, but you'll see after a little while, it's just machine code. So this machine code was produced within the Hall 4 theorem prover and proved correct there, and then exported just as machine code like this. And then, of course, I should mention how was this done. So there's a bit of background. Arthur Shargrove developed the CFML, which is a program logic for reasoning about OCaml code in COC. COC is a different interactive theorem prover. So an intern, Armael Guignot, came and adapted that to CFML to CakeML code for Hall 4. And then Son Ho has implemented more things, significant proof automation on top of that. And this is what Yonkiam used for verifying the more performance critical parts of the LPR, LRAT checker. And I think I should, well, and this can go further. We have it running on a verified CPU on an FPGA and so forth. So we like to verify as much as possible. So this is my PhD student, Andreas Löw, developed this. So I rushed through some parts, but I want to sort of, the message here is that, so get in touch if you want to collaborate on a verified checker of some sort. So yeah, I and people around me have experience and tools for doing these kind of things.
So much, Magnus. This was great. And now, so we'll soon take a break, and then we'll come back for those who are interested with a more technical discussion. But before we take the break, do we have any questions, comments from the audience? So the chat seems to be silent, but so what I had, okay, I don't know if this is a question for the second half, but you showed this whole tool chain where I have this verified CakeML compiler, and then finally I get like a code and a proof that the code does what it's supposed to do. So one question, let's see if I can get this right. Like, suppose I totally don't believe your tool chain. Okay, like you know, these people giving in Gothenburg, you know how they are. But like I see the code, and there's this proof that you have in some certain format, and so maybe I have my own proof checker that I believed in because I coded it up. Like, do I need to believe in your whole tool chain, or can I just take the machine code and the proof and just independently verify that? Does the question make sense?
Yes. So the proof is a little bit complicated because these Isabelle Hall and Hall 4, well, Isabelle actually can produce proof objects, but I don't think it's used much. But Hall 4 doesn't produce proof traces. So it's someone compared it to like if you develop a proof on a whiteboard and you sort of write your statement, this I've now proved, and then I've proved this and that, and you keep on erasing the thing above. Because that's how these proof Hall 4 works. It doesn't keep track of how you proved it. It just keeps track of the statements you have proved so far.
So I can't just come at the end of the lecture and look on the board. I have to be there for your lecture.
Exactly. Yes. Which is a bit complicated in case, yeah, if you only see the conclusion of the lecture. So there are ways of proof logging. For instance, producing these open theory article files that we have a separate checker for, but you can then import into other provers. I don't think that technology scales sufficiently far, but yeah, so that technology is sort of has the promise of one day producing this kind of thing that you can get a proof that you can check somewhere else. If you don't trust Hall 4, you could run it in Hall Light or something like this.
Okay, thanks. Any other questions before we take a break?
For the LRAT checkers, like how much is checked in terms of like parsing the input? I mean, like somehow we have the file format, right? But somehow like these numbers mean variables, but like how do you connect these? Or like how do I know that there is not like, I don't know, some random strings that make this tool behave very strangely or something? Does the question make sense?
Yeah, it makes sense. I don't remember, maybe Yonkiam remembers how much we actually proved of that, the parsing. I mean, we tried to be careful and we specify, but sometimes in parsing, it almost, the specification and the implementation sort of overlap very much. And yeah, there can be problems when that happens. Yeah, but maybe Yonkiam has something. Yeah.
Yeah. So, I mean, in this setting, actually, sort of there's a nice thing that I think Magnus also mentioned is that in the case of set proofs, there's a very nice spec, and the spec is just that if my program say outputs like that this formula is unsatisfiable, then it's really unsatisfiable. So in terms of the proof, you know, it sort of doesn't affect the correctness in the sense that if my overall proof says that, you know, if my total output is unsatisfiable, then the formula is unsatisfiable, then like sort of the correctness of the LRAT part sort of doesn't really matter.
What I worry about is that you parse wrong. Let's say you parse the formula wrong. Let's say you parse in the formula, you pass the empty clause, which isn't actually there. Then it's easy to say unsat, and then the proof will go through trivially because, like, yes, of course it's there, right? But it wasn't there in the first place.
Yeah, I was going to get to that. So like, I think the LRAT part of it is fine. But so for the CNF part, we actually have some correctness theorems in a form that says if we parse the DMAX formula, so that's the sort of the standard format for CNFs, and we parse it and we print it out. I think the printer is the left inverse of the parser. So if we parse the formula and we print it out, it's guaranteed to parse back to the same formula internally. So yeah. So I mean, is that actually? Yeah,
that's a nice idea.
I don't think that guarantees that it doesn't parse the unsat incorrectly, but I guess you do need a standard specification of DMAX, you know, overall too.
So
definitely gives more confidence.
So whatever the parsing is, it is like a one-to-one function, but it could be like, I don't know, flipping the formula in some weird way. But if so, it does it consistently.
Yeah, I think so. I mean, it's basically it's proved to be left inverse to the printer. Yeah, so if you have formula, you print it and parse it, you get the same formula back. Yeah, I think.
Which could, if your like presentation of like contradiction is like an actual clause, then this wouldn't catch it. But I guess this is very unlikely to happen.
Yeah, I mean, I tried to specify it in a way that matches what I understand of DMAX, but you know, I could have got.
I mean, the specification is not that difficult to like really make mistakes, but I think it's like, it seems very difficult to get this connection between like this text file and the actual meaning of the formula.
Right. Yeah. Yeah. I mean, at the end of the day, you'd have to have a specification of the DMAX format, you know, in order to say something about the correctness of that part. Yeah. But we can talk a bit more about that.
Stefan was hinting at the fact that some people might have once accidentally parsed empty lines as empty clauses. And this gives you a very good performance.
So, but yeah, so I think we should very soon take a break. I have just one final question. Like it could be though, like hypothetically, it could be that I give a fully correct proof, but like, I mean, I guess a proof checker that always says, no, I don't think this proof is correct, would in some sense be conformant to what you claimed it does, because, you know, it's just, if it's accepting, then the proof is correct. But do we have any guarantees that in the other direction, correct proofs will be accepted? Or is it more like a social observation that, hey, it always works? Like, so it is not only like if it works, it is guaranteed to be correct, and just observationally, it does work. And so it is useful.
I would say that, so Jan Kerm maybe has something more to say, but I want to add that, yeah, it is more by experimenting that you notice that it's not a trivial implementation. Because the statement is of the form that if it said it's okay, then it really is okay.
Yeah, I think it also has to do with the verification effort. Like, I mean, from I guess my perspective, it's just like, well, the thing that we're really interested in is the soundness result. And I mean, I believe most of the implementation steps should preserve the correctness of, I mean, the completeness of the implementation as far as the original proof system goes. But I mean, we just didn't verify that because that's not sort of on the critical path, you know, towards getting.
Yeah, no, fair. I mean, I'm totally with you that soundness is the hard part. I'm just sort of trying to understand the exact ramifications. So good. So should we, let's see. So then let's take perhaps a 5 to 10 minute break.
Oh.
Okay, good. So we are back after the break. For the second half, the technical discussion. Where I don't know, we'll see what we'll talk about. Maybe some of the demos that we didn't have time during the first half or whatever. Anyway, I was thinking about giving the floor to you again, Magnus.
Oh, okay. Yeah, I hadn't. I mean, I have skipped various things, but I'm not sure how. What you want to see of them. So
I would have some questions more first that
sure.
I came up in the break or forgot before. Like first two high-level questions, like why are there so many interactive theory improvers?
I think one of the reasons is that someone mentioned to me like this, that once you've been in the business long enough with interactive theory improvers, you realize that all of them have faults, and then you feel like, okay, I'm going to make the best one ever, and then each sort of each person who's been long enough in the business makes their own, and some of them catch on, and that's why we have many.
I guess
I would
similar
say
with programming languages. I mean,
yeah, I think so. But I would say there's no clear winner also. So so that's why it's not like everyone should use one. It's just like programming languages too. There's no ultimate programming language.
Or SAT solver.
Yeah.
But there are like a few generally accepted and respected ones, which are like everybody would agree that these are good tools.
Yes.
Or all of them. Or
I mean, they have the same input, like they're exchangeable. I think like interactive theory improvers are not immediately interchangeable.
Exactly. Yeah, they're not so easily interchangeable, especially as you make any development. Suddenly it depends on a lot of libraries and so forth, and specific ways. Like, yeah, like Coq, for instance, has dependent types and completely different logic from Isabelle Hall and Hall 4. So it's harder to migrate between.
So what about Milawa? I mean, this concept of extending, I mean, that seems like really cool, but also useful to extend the core. But is it like unique to this?
So I think it is unique to Milawa to some extent. Certainly that way of just switching the proof checker, that is unique, I believe. However, some people have said that, well, the way computation is built into provers like Coq and Lean means that actually they can do something somewhat similar already, just due to reflection and fast computing of the functions inside. But it's still a little bit different, because you trust the reflection mechanism a bit too much, I think, sometimes, for the fast execution of your logic functions. I'm not sure if I'm making much sense, but yeah, it's a bit unique to Milawa in that way, at least. These Hall 4 and Isabelle Hall, they tend to be very conservative with the logical kernel. You can't just swap it out for some better one midway through execution.
So I think we can certainly, I mean, there might be quite a few questions lying around that we can discuss for a while. I know in terms of stuff that we didn't see, yeah, so some of the slides you skipped over in general, but would be interesting. One thing that I think for me would be interesting is to understand a bit more of this, like how this verified proof checker for a SAT solver is like, what does it mean? So I understood that, I guess the SAT solver runs, it produces a DRAT proof, but the DRAT proof is not very informative. So you annotate it, and that's outside of the tool, I guess. And this is where you get this LRAT proof, which is sort of DRAT with extra information. And then once you get the LRAT proof, then like you take over but what's like happening on the logic side? Like, what is the logic in which you're reasoning about these proofs, and what are the properties you're proving of them? If that question makes sense.
Yeah, I think it makes sense, but I think Yong-Kiam is the right person to answer because he did most of that.
Yeah.
Or all of it, really.
Yeah, sure. Let me actually find if I have some slides too. That would be easier to.
While you're looking, we can also take like other questions if there were.
Yes, I had a question. How afraid are you of cosmic rays? Like we can have bit flips in CPUs, right? And I guess if you have like the Milawa system, which like builds up and swaps out, and like the proof goes through only because there was this bit flip at like a certain point, and now you swap out the core, now you have like an unsound core, right?
Well, I would say it's much more likely that, as with any computer program, that if one bit flips, it crashes in some way, and you realize that. That's also with proof checking. It's your proof. If you, by some crazy luck, manage to get an incorrect proof through due to cosmic rays, you're not going to have that luck twice. So that'll be detected.
But I guess you should like check the proofs multiple times then, right?
Yeah, you could do.
In practice, you do check it multiple times while writing it. So, I mean, you write the proof and then you run the same proof over and over again. So I've never seen, when I write the proof, I run it at least, I think, 10 times before even, because in practice, you will run it several times.
All right, sure.
So I have like some slides from the talk I gave at Takas. I just briefly share the screen, I guess. So, I mean, here is the sort of setup, right? You have, can you see my mouse pointer, by the way?
Yes.
Okay. So I think most of us here should be familiar with the setup. You have some set problem, and you kind of give it to a set solver, which tells, I mean, classically it would just tell you unset, right? And then without any extra information. So I think one of the trends that in the set solving community, where they started looking into, for example, having the set solver generate proofs. So so it doesn't just tell you unset, it also tells you that why it's unset, right? So basically a proof in LRAT format is sort of the state of the art for set solvers. And then, well, what happens is you can give this proof into a proof checker, which have been implemented. So I think you mentioned LRAT trim, which is written in C. And basically the input to this proof checker is your original set problem and the proof, and it tells you whether that proof is a valid proof of unset's viability. And so kind of building on this, I think the question is like, if we didn't trust sort of this output in the first place, why are we trusting this, that this tool is correctly implemented, right? And then there are many ways to answer that, right? You could inspect the code for this checker, but the way that sort of we have sort of approached this is to say, well, maybe instead of doing that, we could maybe have a verified proof checker, which kind of now asks the proof checker to check whether it's a valid proof, and if it's a valid proof, it also kind of expands the proof a bit, into the LRAT format. And now the verified proof checker, well, it takes an LRAT file. It also takes the sort of set problem, and then it tells you whether it's a valid proof. And I guess the question was, well, what's sort of verified about this proof checker? Is that the correct understanding? Yeah.
Yes, yeah. So like understand, open the hood of the green box there and like what's going on inside.
So I can show you the correctness theorem, but I don't know whether it's on this slide. So let me just double check. So anyway, like, by the way, I just want to mention this slide as well, which was So I think the sort of the contribution of this, the work that we did was to try and get this verification further down than what has been done before. So I would say what came before us was that people have already tried verifying these proof checkers, and I think one of the contributions that ties in with what Magnus has talked about is we sort of took this verification and got it all the way down to sort of verified machine code. Rather than verification at a source level, which has been done before. And of course, we also kind of took a stronger proof system along the way. So let me just see if I have the actual theorem that we proved about, which I don't have on the slides. So I need to find the paper.
Just out of curiosity, Jakob, is your question? Isn't your question more like, okay, I want to do the same again, where do I start? I mean, what is the first line I should write in the proof assistant? Because the question sounded to me a bit like that.
Maybe, no, I mean, there's certainly a hidden agenda in the sense that we want to do this for other combinatorial solving paradigms. But I'm also curious, like, as to like we saw this example with this toy source language that was adding things, right? And we compiled it to some kind of machine code, and then I saw a correctness proof, and I was sort of, what does that look like for a verified SAT solver? Like, what is the, what are the properties? What language are we using to reason about things even? Like, and then I guess I would like to understand how to extend it, or find someone who's nice enough, who's interested in doing it. But...
Right. So I mean, if you can see my share screen now, I would say the meta logic or the logic that we're using to verify this thing is actually the same logic that was used to verify the CakeML compiler. It's the Hall 4, the higher order logic as implemented in Hall 4. So what we've proved is a theorem in the proof assistant, the same proof assistant as the verified compiler that Magnus was talking about earlier. So, and this is actually the sort of the correctness theorem that we have for the checker. I mean, it's a bit complicated, but I can sort of walk you through the main parts of it. So kind of basically what it's saying is, if this is sort of saying that you successfully run the tool. I mean, it's sort of encapsulating a lot of assumptions. So this is one of the assumptions, is that you successfully run the tool according to you exported the machine code, you run it on a machine that satisfies sort of the, I guess in this case, x86, x64 model that you have. Then
and you're running it on a concrete input, like somewhere there you have a proof and a formula.
Yeah, well, so in this case, everything is sort of stored in the file system. I mean, in our setting, we sort of verified it down to machine code, including the interactions with the command line and the file system. So so actually this is sort of the internal model of the class of the command line, and this is sort of the model of the file system that we have in CakeML, basically. So of course those are also assumptions on how your OS behaves, but we have a model of how those behaves, and then basically the code is going to interact with it's going to interact with the real system. The real code is interacting with the real system, but sort of in our model we are interacting with these internal models of the command line and of the file system. If that makes sense. I mean, Magnus could just tell me if I'm saying something wrong. But anyway, like, so this is sort of just one big definition that sort of encapsulates most of the assumptions that we need for running a CakeML program. And what it says is, well, if these assumptions are met, then, first of all, in blue here, we are guaranteed that the program never crashes. It might run out of memory, but it won't sort of run into a seg fault, for example, right? It's guaranteed to terminate successfully, maybe with out of memory error. If I mean, these proofs can be quite large. It's possible that the program runs out of memory. Okay. But I mean, and this is sort of a standard thing that you get for CakeML programs. Okay. But the interesting part is, well, how do we say something about the correctness of this program, right? So this is sort of the correctness part that we have proved, the soundness part that we have proved, and it's a bit long because, well, it's sort of the tool right now. It has a lot of different options. I think Magnus showed one option, which is to say just checking unsatisfiability, but there are things that have that other things that it can do. For example, if you just give it the formula, it will try to parse it and print it, and you can just visually check that you actually got the same formula out. I mentioned earlier that when you parse the printed formula, you should get the same formula out. But that's
so the interesting case that we care about is like command line length is 3, because that's when you're actually verifying a proof.
Yeah, exactly right. So that's when you. I mean, the 3 here is just the usual sort of. It's actually 2 arguments, but the first argument is always the name of the program. But then what it says is, well, if the output that you see on standard out, according to the file system model, if the output is this string s verified unset with a new line character afterwards, then what you're guaranteed is that the first argument you pass on the command line is a file name that is valid in your file system. And furthermore, if you sort of read that file and you parse it with our definition of parse Daymax, so this is one thing that you would have to trust, like we parse it correctly in what we claim to be the Daymax format. Then, well, the parser returned a formula. This is a CNF formula, and it turns out that let me erase it. And it turns out that this formula is unsatisfiable according to the definition of unsatisfiability that we have defined in the logic. And of course, the definition is just that that there's no satisfying assignment. There's no way of setting the variables to true or false, so that the formula overall evaluates the true. So what it says in a nutshell is basically, if you see that your output is this string, then you guarantee that the formula that you put in is unsatisfiable. So this is sort of
so just to rephrase that, like if I see verified unsat, then whatever is like array item 1 on the command line, when parsed, results in a formula such that this formula is indeed unsatisfiable, provably mathematically. That's sort of
unsatisfiable according to our definition, I guess.
Yeah.
Which, I mean, the definition is it's something you can inspect, but I mean.
And then we have to inspect it, but the definition would hopefully capture the understanding that somehow, however I set the variables to true or false, there's a violated constraint or something like that.
Yeah, exactly.
Okay, and now if you prove, and how, like, if we focus on this, like, how would you prove this command line length 3 part? Is it like by some kind of induction over the file that you read, or like if we like go a bit deeper?
All right. So I think
that's what I don't know if it's a good question, or maybe this leads too far, but that was sort of, this is exactly what I was trying to understand, but like, what goes inside this proof?
Maybe your question is like, I like Matthias' formulation of it. If you were to sit at proof assistant, what are you going to type to build this thing? And maybe that's another way of phrasing your question. So maybe I think you should.
Maybe really, I don't know what my question is.
I would maybe start from like the pure version only. Like Young-Kim had initially a pure algorithm version only, sort of an easy to verify. That's the sort of idea of the checking. And then there was separately sort of an imperative fast version that ran it well. so to say. Was that right, Joachim? Because the first version wasn't this imperative thing.
Yeah, right. So, I mean, I can share the screen again, actually. I do have, so the high level setup is like what Magnus just said. We kind of sort of take the verification in a few steps, right? And what happens is you sort of start with you start with by defining things like what it means for what it means to be a CNF, like what is a CNF, and then you define what it means for a CNF to be unsatisfiable, which is the unsatisfiable that you saw in the theorem I showed you just now, right? And I mean, so basically you're defining what it means to be a CNF, right? And then what you can do at this level is you can say, well, what does it mean to have a PR proof of unsatisfiability, where PR is a proof system, like sort of an abstract proof system. But no, I mean, it's a proof system, but at this level, it's talking about abstract CNF formulas. So, and then so you can define what it means to be a PR proof system, and then you can say, well, you can define what it means to have a PR proof, and then what you can prove at this level is to say, well, if I have a CNF formula and I have a PR proof at this abstract level, then if my PR proof is a valid proof, then that implies that my CNF is unsatisfiable. And you can do this entirely sort of, I mean, this is sort of a mathematical proof basically, right? And basically what's happening at this stage is we are sort of mechanizing the mathematics part of it. Like we're mechanizing the logic and the mathematics.
So I should think of this as kind of a mathematical proof, but you're writing it very carefully and informal notation and specifying the logic kind of.
Yeah, well, yeah, you're specifying in the logic, and I'm just writing it down actually. I would say this level is already being verified. So the definitions and everything is being checked, you know, by the proof assistant already. Oh. So but this is sort of at a high level where you're sort of, I guess this is sort of the first thing that you do. I think this is even before what Magnus just talked about, which was what happens next is, well, we sort of have this abstract stuff. What we can do next is sort of
maybe you could comment on what is an abstract CNF. I mean, compared to a concrete CNF.
Right. So here, for example, you can write down. I think. I mean, what's I mean, you can write down,
it's the type is more concrete.
Like, so you can write down clauses as, okay. Let me just. Well, okay, so I think it's represented as alpha set, but we can think about, let's say, we can have a set of variables, right? And that's sort of the type of a clause, right? A clause is just a set of variables. Well, no, it's actually a set of literals. So, sorry. So, and a literal is just either positive or negative variable, and that's the clause. And then you can talk about, so this is sort of a clause. And then we can have a clause set, and then that would be our formula. Right. And then I mean, and the notions of sets are available in the logic. So what we can do is we can define well, I guess in this case just a type abbreviation for a clause being a set of literals and a formula being a set of clauses. And what we can do is we can give meaning to these. Well, we can give meaning to what a formula is and what a clause is. And the meaning in this case is, well, given an assignment to the literals, then a clause is satisfied if at least one of the literals is assigned to true, right? And that's the satisfying a clause. And then if a formula is satisfied if for every clause in the set the clause is satisfied by the formula. So I was just looking at my
That means that, okay, so this is already, so I think I understand. So the way I understand it is like the proof assistant is actually, I mean, it's definitely powerful enough then to understand, like, because again, how do I like think of a CNF formula? Indeed, I think of it as a set of clauses where clauses are sets of literals. So at this level, I'm sort of talking about formulas the way I would talk about them. And I guess if I want to use the resolution proof system and resolve two clauses, I would say, well, that's the, you know, if I'm resolving over X, I take the union of the two clauses, but then remove both X and the negation of X. And the point is, what you're saying is, I guess, then, and all these kind of reasoning, the proof assistant is already intelligent enough to like understand what I'm saying. And at this level, it can already prove that what I'm saying, like, for instance, it could probably prove that the resolvent is implied by the two clauses being resolved because it knows what satisfiability is, and a satisfying assignment to the premises implies the conclusion. And then sort of what you're going to do is you're going to like get more and more concrete, but inside the proof assistant. Is that sort of how it goes?
Yes.
So wait, are you doing a deep embedding or shallow embedding of the logic?
In our case, it's a deep embedding actually. But I just want to I think what Jakob said was mostly right. Except I think in the proof assistant is not sort of. I just want to be clear that it's not sort of automatically doing all of this. You sort of need to tell it what you want. So, for example, like you said, if you want to know that the resolvent is implied, then well you state that as a theorem, right? That the resolvent is implied by the resolution rule. From the two clauses that you resolve, and then you can state that as a theorem, and then you be able to prove it. But the proof assistant is sort of smart enough just to understand this definition. But let me just share my other screen, which is this. So my script isn't as nice as Magnus's, but I don't have it like set up in a, but anyway, like, so and what Matthias, I think Fleury, said was that I would say this is a deep embedding because I mean sort of we are defining well.
Could you quickly mention what the difference between a deep and a shallow embedding is?
Yeah, so
or is
I
this too
think
complicated.
Well, so a shallow embedding is if I let Magnus say it.
Yeah, deep embedding is when you have the syntax available in the formalization, so that you can then, for instance, write a function that traverses the syntax and does something to it, while a shallow embedding is you more directly embedded it. So a shallow embedding would be, for instance, you would say, okay, I need a literal that can be a Boolean variable in Hull, so let's make it a Boolean variable. But it's not something, then within the logic, you couldn't traverse it because you haven't actually formalized the syntax. You've only formalized the meaning of it. Is that?
Yeah, I think I get the idea, yes.
So whereas deep, somehow in parallel, you would have, you know what these things mean, but you also have the representation and you can sort of jump back and forth between the syntactic object that is the literal and somehow the meaning of this literal. Is that
yeah, exactly
way to think about it?
Yeah.
Yep. So I mean, in this case, this is more or less a deep embedding because I mean we have, I mean, except it's not quite as executable as what we have later on. But yeah, it's a deep embedding which roughly okay, so this is the type of literals basically. And then you can see, well, a clause is a literal set, and then a CNF is a set of clauses. And the A here is just a type variable, but that's not like super important for us. And then we can also define what it means to have an assignment. It's just a mapping from okay, A is the type of variable, so variables to booleans, and then, like I said, you can define what it means for something to be satisfiable or unsatisfiable, and let me clear. And this is what you would, I mean, this is at the end of the day, maybe this is what you would want to inspect, like this definition, which appears in the theorem, right? You would go back and inspect, what it depends on, and so on. But what it says is, well, it's unsatisfiable if it's not satisfiable, and then what it means to be satisfiable is, well, there is an assignment W such that the formula FNL is satisfied by W. And then what it means to be satisfied is, well, given an assignment, for every clause in the formula, the clause is satisfied by W. And then what does it mean to be satisfied by a clause? For a clause to be satisfied, well, there is a literal such that the literal is in the clause and the literal is satisfied. And then, okay, what does it mean for us literal to be satisfied? That's the definition, and so on. So,
okay, and just to curiosity, as I'm playing around with this and trying to understand, suppose that I, at the top line, line 28, I decide that an assignment is a list of literals instead. Like, because sometimes I maybe want to think of, well, it would have to be a set of literals where you never have a complement, I guess, but let's ignore this for now. And suppose I want to do this, but I want to leave the rest unchanged, then I guess I would change, like, satisfies literal. That would then be the definition somehow, that it's satisfied if one of the literals in the assignment is actually the literal I'm looking at. And then satisfies clause and satisfies formula would sort of be the same because they all go down to what it means to satisfy a literal.
Yeah, exactly. So what you would do is, I mean, that's actually what happens like in the next step, where we sort of go to a more concrete version of this. So I mean, sets are, I mean, it's not necessarily, even in this definition, it's not necessarily even a finite set. But when we go to lists, for example, or when we want to think about a list of literals, then yeah, that's actually what happens in the next step when we go to a more concrete sort of instance of this setup, I think. Yeah, but I think you're right. Like what we would do here is just basically modify these lines to kind of talk about what it means to be satisfied according to this new representation of an assignment, and then the rest of it would basically be unchanged. Yeah.
Maybe also telling is if you could show the proof system for the abstract.
Yeah, that might be a bit more messy, but let's see if I have.
And would all the steps, like going from step 1 to step 2 and then step 3, these different level of concreteness, do they all involve like original part, or is it like somehow once I have my high level definition, what we're seeing here, correct, then I somehow can piggyback on stuff that you guys or other guys already did, or like how does this work?
Yeah, I can go back to that in a bit if I just because I need to share back the other screen, but anyway, like I just want to mention that, yeah, so given these definitions, you can state theorems about these definitions, and you can, for example, well, prove a bunch of different theorems about it. In this case, and we have different ones, and I think this is the sort of the main theorem that we used, I believe. But I mean, it's basically saying, it's basically mechanizing the sort of the correctness of the PR proof system. Yeah, it's a bit of a mess, but yeah, this is what it would look like. And then sort of you have a proof that is in that script that Magnus talked about. It's basically not very readable unless you're sort of looking at the proof state sort of interactively. But I mean, I think this is pretty common if you're using a proof assistance system, unless you're maybe using Isabel. But well, with the what's it called, the language, yeah, yeah, but yeah, otherwise, yeah, it looks something like that. So, and then basically you mechanize the correctness of the proof system in sort of this way, and then these proofs, I would say, are more are sort of the manual part of it, right? Right, but yeah, I don't have anything like super nice to show.
Yeah, I'm just curious. So maybe this is taking us way too far, but would it even be possible? Does it fit on a screen full? If I want to see the proof that a LRAT clause can be added without changing the satisfiability?
That's what you just saw, right?
Is it? Yeah. Well, I was.
Yeah, I mean, I don't think that was a LRAT. I mean, so I proved it in 2 directions, but I think this is the proof.
Wait, isn't the theorem more general than just LRAT?
Yeah. This is a theorem for PR.
It's PR.
I think. Yeah.
Okay. Yeah, but it should still be.
Yeah, but I mean, it's okay. If you reduce the
But
font
I think
size,
don't look
this,
at the
but-
proof. Like, I think let Jacob have some time to look at the theorem. I think that's what's important, or no?
Yes.
I think because like the proving of this detective theorem is not so insightful. I think it's more like
You're saying that the theorem we're seeing now is that the PR rule is like, okay. Is that the theorem statement?
Yes. So
Yes.
I think the conclusion of the conclusion of the PR rule is that a given clause C is redundant for a formula.
Where we have defined what redundant means somewhere.
Yeah, somewhere above. But
and would you help us parse these for like from 290 onwards? What does it?
So okay, so the notation is a bit weird, but so I think S is a, well, in the comments it says it's a partial assignment to literals, and in this case I'm thinking about a partial assignment as a set of literals. So
wait, I think it's called a witness, right? I think
exactly.
S is called a witness in the literature.
Yes.
Yeah, exactly. This is W in the literature. This is what I was saying. It's mechanized a bit weirdly, but yeah. Basically, it's saying that I mean it satisfies the clause, and then this thing is this implication. So
here we have already switched to an assignment being a set of literals, actually, right? Because that's why you're taking intersection.
Yeah, for this particular theorem, I stated it in that form. Because I mean, I think it happened to be convenient to talk about sort of partial assignments that allow you to sort of reduce a formula under the partial assignment. So that's sort of what it means. And it happens that also if you have a clause which is a set of literals, then the blocking assignment, I think is what it's called. Maybe I'm wrong about the terminology, but that is basically given by the negation of the clause. Basically negate every literal in the clause.
Okay, so what you have on line 293 is there you say that, well, you have the formula plus the negation of C, and this implies F under the restriction of the witness. So that's exactly where we have the, okay, yes, oh, it's even written there, I guess.
Yeah, so A is just the this thing is A basically. It's taking C and then flipping every literal in C. That's the sort of the blocking assignment. If I remember the term correctly, it's the blocking assignment. So and this is just saying that take every literal in C and then flip it. So this is the theorem statement, and then I mean the proof basically I follow Myreen's paper at I think the JAR paper or something.
Oh, so then you need, okay, so the proof assistant won't figure this out, but basically you take the paper where this is written down carefully and you sort of translate it in the formalism that the proof assistant understands, and then at the end everybody's happy.
Yeah, exactly. For this part, I think it was mostly following the paper. I mean, even I think this is exactly the choice of the assignment that they gave in the paper, if I'm not wrong. But I mean, in this case, it's a bit difficult to read. But basically, what it says is assign according to the partial assignment. Otherwise, use the old assignment. But so this is. I mean, this part is, I guess, manual. Except in this case, we have the proof already, so we just mechanize it in a way that, like you said, the proof assistant understands. I mean, I guess this
is super neat, no? Fantastic.
I mean, this part is all in. I would say it's still sort of at the level of the mathematics, I think, or the logic. But is this part clear now? Okay, so. I think I go back to the other question, which was, what happens here, right? So we have this sort of the mathematics formalized already. I guess the next step is to try and move it towards implementation, which is sort of, I guess this part in yellow. And I think the question was whether we can reuse tools. So the answer
are we done now, or do we have to work hard in step 2 and step 3 also?
Yes.
Kind of.
So
my question.
Step 2 is not super hard, but I think step 3 is the one where you do put in a bit more effort. But step 2 is actually, I think, what Magnus already I think you did mention about the translator, right, earlier in your talk.
Yeah, I did.
Yeah.
Yeah, the connection to this, maybe you could clarify.
Right. So far we have this representation as sets, right? So one of the things that we want to sort of now do is to say, well, how do we want to implement it? Okay, so one implementation is, well, let me represent my CNF as a list of literals, sorry, a list of clauses, and a clauses be lists of literals. And so that is sort of a concrete representation. And then we would also have to talk about what does it mean to concretely check a PR proof. So how do we check something in terms of lists instead of something in terms of just the set notation, right? How do we take, for example, I guess the intersection of a clause with an assignment, right? I mean, in terms of lists, right? How do we write that down in terms of lists? So, and you can sort of write that as functions, and basically the thing that you need to show here is that somehow you need to show that you need to show that these steps are connected, right, in some good way. That basically you're implementing, you're representing the CNF in the correct way, and then you're implementing the sort of proof system in the correct way. This sort of implementation you can write down and you can prove, and I think that part needs proof, but I mean it's more or less sort of writing it down in just a more concrete way. But what Magnus mentioned is that once we have written this part down, actually from here we can go down to the machine code already, more or less. In that we would be able to use this tool called the translator, which takes these definitions, turns them into CakeML source code, which we can then compile down to machine code already from there. So that's the part, in the sense that the part that we can reuse. So I guess this yellow box, we can actually take this down to code already from here. And this part is free. I mean, the compiler is already verified. We just need to use that theorem.
Like in the concrete step 2, I mean, a concrete clause, would that still be like an ordered list of literals, or would it already be like a list of integers, positive or negative, or that happens in step 3?
No, it would be a list of integers here. Sorry, I missed that part out. But okay. Yeah, you would choose something that you could actually write down as a, I guess, a C program, or in this case, a ML program.
So in step 2, you're already very close to the Dimex file, except it's not a file, but it is sort of what will be in the file.
Yeah. So that's this representation, but also the checking algorithm here would just have to be implemented over this representation, right? You basically it's almost like you're writing functional code at this point, except these are still functions in the logic, which you would then sort of kind of compile, automatically translate and then compile down to machine code. So yeah, so this part you still have to write, but I guess this big arrow which goes down to the implementation in a source language, you don't have to write. This part is free, but this part is sort of what you have to write. And then I mean, so I think sort of the quote unquote problem that with sort of what we have here is that it's still not as sort of fully efficient as you like, especially for I think especially in the set proof checking setting. I think it's becomes a lot more important to have a sort of a efficient way of checking the proofs. For example, you might want to use arrays instead of functional lists. You want to use arrays with O1 lookup and stuff like that. So and I think that's where I would say most of the verification effort, at least for me, was, because sort of a lot of it was just writing down different kinds of optimizations that used these faster data structures that allow me to make the proof checker faster, basically. And of course, at this stage, we use the sort of CF framework that Magnus talked about earlier, and this is sort of most of the verification effort goes here, because here we don't have the automation. Well, we don't have a lot of automation help. So basically,
just one other concrete question to try to understand. So this is for propagation redundancy. Then there's like further work that has done, I think, something that's called substitution redundancy, where this witness thingy, before it was like it was a partial assignment, right? But now you have exactly the same propagation redundancy rule, except that the witness is now a partial mapping of variables to truth constants or literals. So like you don't take the variables in the formula and map them to true or false, but you potentially also map them to other literals. But if you just sort of define what that means, it seems like, again, you should basically do very local changes, and what you have, this diagram would also work for substitution redundancy, or would there be like...
I think so. So basically you'd say maybe you I guess you extend this proof system to say, well, I can allow either PR or SR, and then you prove the correctness of SR over here. You implement the SR, and then maybe if you need to, then you could also make it like more efficient, through if needed, in the checking part as well. So I mean, that would be sort of the process that I would have taken. If I wanted to extend it, I would go through the same steps again. I would start with the abstract form, what it means for SR to be correct, and then sort of implement it in a functional way, and then think about how I would maybe put in more optimizations if needed to the checking algorithm for that. Yeah.
Except that I guess the proof of implementation might be different, because now you don't necessarily fix things to true, but you accept clauses that are, well, they're not implied by the witness, but once you've used the witness, they are reverse unit propagation clauses. And I guess reverse unit propagation is not so nice to deal with inside this system, because you got rid of it in LRAT, right?
But like what LRAT
but the proof checker, I mean, I guess you could do like
you can just do the same.
Yeah. You could do the same annotation, I guess. Yes.
Yeah. I mean, actually, sorry.
Go ahead.
Oh yeah, I was gonna say, like, so actually we didn't do it for SR, but I think for this, actually this is an extended version of our paper. We actually looked at, for example, can we design a proof system that's, for example, allows you to do parallel checking, and that was the process that we sort of went through, which is kind of think about a proof system that is sort of easily parallelizable, and then talk about, well, how can we implement it here and then here as well. So I mean, in this extended version, that's exactly what we did. I mean, we didn't do it for SR, but yeah. So someone had a question, I think.
Yes, before you mentioned that you have an UNSAT proof given by a SAT solver, and there was a conversion to LRAT. I'm not sure, where does this happen, and shouldn't this conversion step also be verified? I don't know whether this, it's a stupid question, or can you import errors when transforming from an UNSAT proof to an LRAT proof, or?
So that part is not verified, and the reason is actually it doesn't need to be verified, in the sense that, if you made an error there in this external tool that generates the LRAT proof, it's still fine, because I mean, at the end of the day, this thing will check whether the proof is a valid proof, and if it turns out to be an invalid proof, then you will say that there's an error. So, and what that means is that so what that means is that, well, it doesn't tell you that, it doesn't sort of how do I say it? So there's no soundness problem is what I want to say, I guess. In that it doesn't incorrectly claim that your output is unsatisfiable.
So I think, Sibylle, one way of thinking about this is like, so you have the DRAT proof, and then you just, for every like RAT or RUP step, what LRAT does, you just have an external tool that you have not verified, and it just annotates which clauses are being used. So you just like decorate the proof with this extra information. And if this algorithm is buggy, then what can happen is that a correct proof might be rejected, but it can never make an incorrect proof be accepted, because what will be checked in the end is like the LRAT proof.
I mean, you can have like the solver can produce an incorrect proof, and then the intermediate tool somehow thinks like, yeah, it's incorrect, but let me fix it for you.
Okay,
and
sure.
Produce the correct proof, and then this gets verified.
verified is the LRAT proof.
Yes.
And if the tool says that the LRAT proof is okay, then it is okay.
So you know the formula is indeed unsatisfiable, but you don't know if the solver did the right thing, kind of, I guess.
I mean, I think that's already kind of happening, right? Because I think in the LRAT proof, you can have clauses which are not used, which are skipped, which are not reprinted. And I think there are theoretically at least cases where, because you don't add buggy clauses, then the proof can go through.
Yeah.
So it's
Yeah.
kind of built in that it's fixing bugs.
Yeah. The rat trim by itself fixes some bugs that you'd get with the rat proofs. Yeah,
So this thing like unit clauses not being clauses.
No, even like
stuff,
let me do some unsound reasoning. I drive a clause, it's not implied. I write a like rub step for this, but I never use this clause ever.
Yeah,
then the backward checking will ignore this, right? So it will not be checked. So like, yeah.
But that would be trimmed already on the DRAT side before.
Yeah, but that's what we are talking about, that thing. No?
Yeah, but I don't know, Sibylle did.
Yeah, I was indeed thinking of the solver gives out an unsat proof and something goes wrong, that it does not become invalid because I don't know the formats. This is the major problem. So that the proof still remains valid somehow, but it's wrong. But seems not to usually be possible.
Right. So I mean, I guess in this setting, as in for the purposes of this work, we aren't interested in the correctness of the proof itself. We're interested in whether the formula is unset or not. So, but if you're interested in the correctness of the proof, then yes, that would be sort of a separate thing. And I think there's been other work that have looked at well, what does it mean exactly to be a full proof?
So it should not return that the formula is sat when you have an unsat proof because it was somehow modified. This was it. Yeah.
Yeah,
no,
but that part is not possible. Yeah.
No, I missed some background. This is okay. Thanks.
I had, I think, a step one question, which is, how much do we have to trust the basic things like resolution? So let's say I was completely skeptical and I didn't even believe that resolution was sound and complete, but I do trust your proof checking system. Is that okay? Have you proved effectively that resolution is valid?
I guess you would prove RUP instead, but or like
Yeah,
this
or
annotated
RUP,
RUP, which
yeah.
essentially is resolution, but
Yeah.
But we discussed that it's possible to prove that, like if a clause follows by the resolution rule, then it is indeed implied. That seems to be easy to prove.
Yes, sorry, I was muted, but yeah, I think yeah, I mean, if the purpose of this part of the mechanization is, let's just say we don't trust the PR as it was written by on pen and paper, this mechanization shows that it's correct, at least according to the way we defined it. The PR step is correct, and in the case of resolution, it would be the same thing, right? We just have a resolution here, and then I mean, maybe it doesn't go to unsatisfiability, but you know, we can prove some property about it here as well.
Yeah, but inside here, like you do believe basic properties of set algebra, you know what a function is, that kind of stuff, you know, inside the blue circle, but you don't necessarily know at all what the resolution rule is. That's being defined and properties of it are being proved if you want to.
Yes.
Right?
Okay. Yeah, I was just thinking if at some point we were to switch to, for example, cutting planes inside there, and we're possibly moving to a system which is less so obvious that you don't need to prove it.
no, I mean, you need to prove these things. I would expect that in step one, there is like actually a theorem that says that these annotated RUP steps or like trivial resolution steps are indeed implicational sound, right?
Just on that, I saw a talk recently by James Davenport, I don't remember where. And basically he was explaining that in the proof system he was trying to get, I think it was CCAD, but whatever. The point is that already the first step didn't work out because it was too complicated to do in a proof assistant, because the theory was so complicated and messy that they just didn't know how to prove it. They tried and they failed already at that level. So yeah.
No, but I think that for our use case, for cutting planes should be fine, and institutional redundancy should be fine, and then beyond that we would have to look.
Yeah, sure. It just can happen.
So I managed already to do addition in Isabel.
Cool.
Yeah. So yeah,
but it took me quite long.
Yeah, I just want to add on to what Matthias said, which is I think in this case as I've been referring to this as the mathematics part, and in the case of SAT is just the mathematics is just propositional logic, and I guess Davenport will probably be working on real arithmetic, so that's a lot. Reasoning of like proving the correctness of the mathematics there is going to be a lot harder, and it also depends a lot on the libraries that you have available, in your proof assistant. In terms of math, Isabel, I would say has a lot more than Hall 4, probably. So yeah, that's one. Okay, so that's like long stories you can tell, but there are many different proof assistants with different sort of math libraries as well. So if you wanted to use one, you also need to be careful about having the correct sort of math available for you, for your purposes, I guess.
So I think the kind of things we would want to be able to prove is, I don't know, like if you know, so we still have you have 0, 1 value variables, and you have integer linear inequalities, and you want to prove things like if x plus y is greater than 1, okay, x plus y is greater than 1, and y plus z is also greater than 1, then I guess x plus 2 times y plus z should be greater or equal to. Something like that. So then you have to, I guess you have to collect coefficients. You need to do some cancellations of plus and minus and stuff. But I guess the proof assistant at this step 1 level, it would like know enough math to add linear inequalities and know that, for instance, a linear inequality that if I multiply it by a positive integer, that's still valid. It doesn't flip, that kind of things.
I think these are things you already want to kind of show, but you have like things like taking the sum of integers in Isabel at least.
No, but I'm asking, yes, but I'm saying, yeah, so integer arithmetic, I assume, but operating with linear inequalities, I guess you would need to prove these things, but it would be within reach, or?
I think so, but Magnus would know more, I guess. But I think also there's even decision procedures for integers, like not decision, but like arithmetic procedures, like tactics that will allow you to prove things like that.
It depends on what level you want it, though, because if it's shallowly embedded, yeah, sure, that sounds perfectly fine.
Right.
But if you want to have it as part of your checker, sort of into step 2 and 3 in implementation, then you'd have to verify that algorithm as modeled in the logic. And I'm not sure is done in Isabel either. I'm sure, Isabel and Hall have decision procedures for linear arithmetic. That's standard. But if you want it to be part of the checker, then yeah, you have to verify it. But by the sounds of it, it doesn't sound complicated though. For basic ones at least.
Like another thing you would want to be able to do is just like suppose you know that, I don't know, 2 times x plus 2 times y plus 2 times z. So 3 variables, and you just sum them up, but with coefficient 2, okay? And you know that this is greater or equal to 3. Again, these are 0, 1 valued variables.
Sure.
Then you actually know now that the sum of these 3 variables is at least 2, right?
Yeah.
And this, I want to be able, my proof checker should understand this, and this should be verifiable.
No, but like, the way you do this is that like you take the cutting planes rules, like we have 2 inequalities and we can drive a new inequality. And now you in the higher language, you specify, okay, what actually is an inequality? So like the way I modeled this when I tried this was that it's like you have a function from a variable to a coefficient that's like can be negative or positive. And I have like a constant right-hand side. So now I have like a syntactic object, right? I have like a function from variables to coefficients, and I have like the right-hand side. And now I can define like, okay, what does it mean to evaluate this inequality, right? In the same way this was done, we have seen here with clauses, right? Like we somehow model an assignment, and then I can say like, oh, like this inequality is true if I take the sum of the coefficients multiplied with 0 and 1 of the variables, then it's greater or equal on the right-hand side. And now I have like an understanding what is an inequality, what is like the evaluation of an inequality. And now I can show that, now I can define like what does it mean to add two inequalities, for example, right? And adding like, this is like a algorithmic thing to add two inequalities. And then I can prove that, well, if I have an assignment that satisfies both input inequalities, then this satisfies also the output inequality. And now I have like this addition rule. And this I can now use, I guess, in my proof. I know that, oh, if the addition rule is used, then whatever I drive is sound, right? And then I know that, oh, for some proof goal, I need like this to be a sound derivation. And I know like, oh, every step's very sound, and this kind of works out. And the same you can do like for the weakening rule in cutting planes, which gives you like this 0-1 boundness, right? Or for like the division rule or situation rule and so on.
Yeah, I mean, I think, well, so I mean, in this case, you would be working with basically a deep embedding, right? And then improving the soundness of those rules for the deep embedding. And yeah, I mean, it sounds like what you said is correct. You basically formalize what the rule is, and then prove the correctness of that rule. In your case, I guess, in Isabel. And yeah, in those cases, you would be, I don't think you would be reasoning about this. You wouldn't be using the built-in decision procedures, but you would be just like reasoning of a 0-1 arithmetic. But that reasoning should be possible, I would say. I mean, even in Hall 4, it should be possible.
You need some reasoning about like summing stuff, that like if you sum both left-hand sides and sum both right-hand sides, this is like, then it's still true and stuff like this. I don't know.
It's all, I think, yeah, my suspicion though is that, yeah, because it's done in a deep embedding, you'll have to, you know, implement much of this yourself, but by the sound of it, it doesn't sound like that difficult.
And when you say a deep embedding, does this also mean that I will somehow have to connect things like, if I have the number 123, I will somehow connect this to the string 1, 2, 3, or the ordered sequence of characters 1, 2, 3, or like
only in parsing, not otherwise. No.
Okay. I guess we've been going on for quite a while. Maybe we should think about how to wrap up this in a few minutes. If there are any extra questions, any additional questions, sorry, or comments.
I mean, if there's time, I would appreciate a brief discussion about the high level, like turning CP into pseudo-Boolean and how we know that that's correct. But I realize we've been asking a lot from our speakers. So
can you repeat? Is turning what into what?
So I work on constraint programming solvers. So here we're dealing with something that's a bit higher level. What I'm doing currently is compiling high-level constraint programming models down into pseudo-Boolean models. And I'm providing a cutting point proof of correctness that the pseudo-Boolean model is unsatisfiable. The difficulty here is I might be given a high-level constraint programming constraints like X is the minimum value in this array of 10 other variables. And what I want to do is produce a pseudo-Boolean model that means the same thing as this. And this is surprisingly tricky to get right.
But like the simple case would be the X might be an integer valued variable between 1 and 10, and then you'll translate it into like a collection of 10 Boolean variables, out of which exactly 1 is true.
Yeah.
And now you want to say that whatever, like before you were reasoning about this integer between 1 and 10, it should sort of, you want to prove that, well, it's the same as using this unary encoding or one-hot encoding. And for instance, the value of X is the same as sum over I times Xi. right? Things like that.
Yeah.
Does that make sense, Magnus?
Yes.
I mean, this feels to me almost like it's more a verified compilation kind of thing, that we want to turn a high-level model into a low-level model. Okay, in this case, it's a constraint programming model into pseudo-Boolean form rather than a programming language into machine code. But
Sure. I mean, yeah. Yeah. So you want the correctness of that translation?
yeah, that I found. So my biggest most of the bugs I've had in writing a constraint programming solver and produce proofs now have not been in the propagation algorithms, so not in the reasoning, but just in the definition of what the constraints mean. So for example, if I'm telling you that, so there's an element constraint, so you're given an array of integer variables, you're given an index variable, and you're given a value variable, and you want to say that the value variable is equal to the look up in the array using the index variable and say it's equal to that. And immediately you run into difficulty. So what if the index variable doesn't actually run over the array, but it runs over a subset or a superset of the array? What if the equality variable has a different domain to some of the values in the array? And I found that it's all very well demonstrating that the reasoning we do on the low-level model is correct, but a low-level model does not necessarily reflect the high-level model.
Yes. So I supervised a project for students that were doing encoding into SAT from pseudo Booleans and so forth. And yeah, they had similar, but they didn't go as complicated as that, but sure. So yeah, I have some experience in supervising that. But yeah. What was your question about it? Like yes, I think I understand what you're talking about now.
I mean, so my main question is this something that I should ever be thinking about, or should I be happy with? Here we have a constraint programming solver, and if you trust that it produces the right pseudo-Boolean models, then you trust it's providing a right answer.
I think it sounds like a good idea to formalize and prove the encoding into the low-level model.
Okay.
And yeah, it all, of course, the complexity of it depends completely on how fancy you want the encoding to be and how complicated the thing you're encoding is. The students that I supervised, they were encoding puzzles, and that was manageable, I think. But I mean, but of course they weren't going to the most optimized encodings either. So if you specialize for certain specific problems at the high level, then you can use very fancy encodings, and they weren't doing that. They were going more sort of general encodings.
So I think we can actually just go to the simple encodings, and then I think our goal here is to use cutting points plus extension variables to actually create the more complicated encodings inside the proof.
Oh, okay.
Well, I guess you have a choice here, right? You can try both and see what's simpler, whether it's easier to like directly do the complicated encoding in the higher order logic, or whether it's simpler to just do the simple encoding in the higher order logic, and then use the proof logging and of the solver like on the propositional logic level to re-encode.
Yeah, I mean, if the approach for the second method, which is to generate a simple encoding, and then I mean basically encode the pre-processing in for the propositional side, I mean that would be less work. I mean, from the sounds of it, right? Because I mean you're not formalizing the pre-processing part. You get that part for free, right, from your checking afterwards, anyways. So
I mean, it depends how difficult the propositional proof is there, but
yeah, but like I mean, if that proof, I mean, if you wrote the pre-processing part of the proof wrong, then I mean that part would just fail to check instead of
no,
Yeah, so that would be, seems like less work, I guess, but yeah.
So I think it sounds interesting. So if you could send me an email and we can then, I can share, for
Yeah, I'll
instance,
do
this
that.
master's thesis, although it wasn't, it was slightly low on technical detail in places, but it starts a conversation.
So
Yeah,
I'm thinking that this is a conversation that should continue,
Yeah.
but I'm taking the opportunity here to thank the speaker again, because I want to switch off the recording. So I guess by now, definitely 2 speakers. Or
Yes, exactly,
more.
2 speakers.
Thank you so much. This was wonderful. It was great to see like how to, to get a sense of this workflow and what the tools can do. So thank you so much. This was an immensely fascinating seminar. Thank you.